Okay, hello everybody, let us begin. We are slowly approaching to the end of our course, so today we will speak about some more specifics related to unsupervised machine learning. In particular, we'll discuss technique called dimensionality reduction, which we started to discuss last week. So I will explain again some example and we'll show you some techniques that we are going to try in our next practical exercise as well, with some additional explanation why it's important and why do we want to do that. So basically, let's cover this topic while we are at it, and accordingly then we will be able to, I believe, conclude in a matter of few more lectures our course. So let's get to the dimensionality reduction. So as I did explain last lecture, let me draw up fast this same example of the Netflix. Yes, we usually, quite commonly, yes, have situation when you have a lot of redundant features which are not necessarily available for all data sets. So in a sense you can say some data points are missing, some entries might be missing in your entire data set, etc., which is the best demonstrated by Netflix movies review rankings, yes, like movie 1, movie 2, movie 3, and accordingly user 1, user 2, user 3, user 4, etc. So not necessarily every user is going to rank every movie in your platform, so some users have ranks for certain movies and others do not. Some might be even don't have any rankings at all, somebody might have only one ranking, etc., etc. So in this sense you have something called a sparse data set, yes, where you have a lot of empty points, a lot of zeros, and what would be a nice idea to do is to somehow, redo this data set, to convert it, transform it, and dimensionality reduction is one of the ways to do so, because here, essentially, if we speak about, let's say, this case of user 3, then we can say that it only has one dimension, because it only provided one feedback, only one review, yes, of the certain movie. While others might have 3 dimensions, others might have 4 dimensions, etc., etc. So not all of these dimensions are necessarily necessary for every user. So because of that, we want to try to, extract the most important ones. And that is also common to some data sets where you have certain correlated features, like, let's say, area of house and, let's say, length of the house. Because you can calculate the area of the house by 2 dimensions, so it's really not necessary to have the length as a separate column to make predictions when you already have area. Yes, so in that sense we would like to exclude, for example, length, and that happens to some other features, like maybe, for example, some data set when you have some, I don't know, let's say credit history or stuff like that, and there, for example, you have a feature of input of age of the person and the fact if he is a student. Of course, age and the fact that he is a student are somewhat correlated as well, because, well, younger people who are students tend to also ask for more credits, and that's understandable. For studies, for example, the same stuff, yes, so they are correlated. And in that case, we would like to, somehow merge together these 2 columns, yes, like column A and column B, into some new column C, which is a combination, I will write it like this, combined A and B. And there are ways to do so, yes. So dimensionality reduction is one of the ways to solve this kind of a problem. Now you can see some more examples of this highly dimensional data, like documents, the same ChatGPT, yes, which operates with words and entire sentences maybe even, yes. And each word can be considered as a feature of your data set, as a dimension with which to work. Same goes for images. You have a lot of pixels, yes, and although the image itself is, we can say, three-dimensional, yes, because you have a red color, two-dimensional picture, you have a blue color, two-dimensional picture, and you have a green color, two-dimensional picture. So in a sense, the image itself is three-dimensional, but it consists of millions of pixels, yes. Well, even if you say take not really high resolution image, but low compression, that means you need some high quality, then you will have high file size, yes, in megabytes, and megabytes are already millions, yes, of pixels. So imagine then we go to the movie, yes, where you have not single such a picture, but actually time series where every second you have, like, let's say 60, 50 or whatever number of these images, and each of these images consists of hundreds and thousands and millions of pixels, yes. So again, not all of these pixels are necessarily required for making classification. Same goes for DNA analysis and some genomics, yes, where we have thousands of genes, and not necessarily every single gene is providing the same amount of information to your, let's say, if you try to study some susceptibility to a certain disease, yes, so only specific genes are most important in that case of study, yes, and you want to filter out all the others. So those are some examples of the problems involving high dimensionality, yes. It's like comparing when you were living in small village and then you moved to New York, yes, how many different people, how many different situations happen to be, and well, at the beginning it's difficult to orient and all that. And, this is very similar, yes. So, what are exactly problems with high dimensionality? Why is it bad, and is it even bad? Yes. So first of all, the main problem is maybe not even in how difficult it is to work with this data, because, you know, having let's say table of 5 columns to work with for people, yes, to analyze this table and make some conclusions is much easier than having a table of working with million of columns, yes, and you then don't really even know which columns are more important, which columns are less important, are they at all relevant to this data set or not. That is, of course, also interpretability question, but it's more related to us as people and our certain limitations of our brain and all that stuff, which is also a problem, but let's maybe focus on some more technical problems, like having multiple irrelevant columns in your data set might actually make your predictions worse. Yes, so that is the problem of underfitting, overfitting, and all that stuff that we have been discussing. So it's even actually making your algorithm perform worse because you have some unnecessary, irrelevant features. Yes, that is why we do some regularization technique. Yes, that's we have involved multiple times. Another problem is, of course, that you really have to train this. Yes, and if you have a lot of data and you have some specific algorithm, let's say of complexity O of n power of 3, meaning that, let's say, amount of memory necessary to store all of this data is third degree of your amount of data points. So you have 1 million of data points, then you will need 1 million on the power of 3 memory space to store all these results, which brings you sooner or later to limits of our technical means, yes, and makes you somehow split your problem into smaller parts, which again may not really cover the entire picture and be somewhat limited of use. Yes, so some algorithms definitely were of this complexity. We were discussing last lecture some of them, and you have seen that some algorithms are really that demanding. Yes, that is a problem as well. Now, if we return to regularization, then we can say that we reduce effectively or actually dimensionality reduction by using different levels of regularization. And that level of regularization was as simple as, let's say, in our neural networks when you were subtracting our theta coefficients, yes, like this, that is level 1 regularization. Level 2 regularization is when you subtract squares of these thetas. And that's basically as simple as that. Yes. Now, what we want to do right now is to say, okay, now we understand that some of our inputs might be unnecessary, some of our inputs might be partially empty for certain data entries, some of the inputs might be correlated with others, yes, and what we want to do now is to somehow combine multiple inputs into fewer number of inputs. So let's say you have 100 inputs combined into, let's say, 10 inputs, which are linear or non-linear combinations of your inputs. So there are two ways to do this. Yes, first one is making some linear combination, which is usually some kind of a summation or a regression problems, yes. And another way is to do something like non-linear combination, which is more complicated and most often used to better visualize data. So, for example, in our next practical exercise, not exactly really sure what specifically algorithm we are going to study, but as one of the steps, we are going to do some dimensionality reduction. So that is going to be our step 1. We'll have our handwritten digits, like 1, 2, which are normally 20 by 20 pixels, as you already know from our previous practical exercises. And what that means is that in total, each picture is represented by 400 inputs, 400 pixels, yes, which can be from white to black in different variations. So what we are going to do is to run some dimensionality reductions, let's say to have 25. They are no longer pixels, these are now fragments of picture or something like that, yes, certain sections of your picture which are created as a combination of your initial 400 pixels. So you can say very roughly that for each of these 25 features, you are going to group something like 16 pixels to form just one of these 25. And then the second step is going to be to train some algorithm. Yes, let's say a neural network and see if this procedure actually changes anything. Will it still be able to make predictions accurately? Maybe it will become even better, maybe it will become worse. This is something what we will study. However, I still am in doubt about what specific algorithm we should try next week. Maybe we will do reinforced learning, just to, you know, see what it is exactly and also to make it in time as an additional material for you to understand, because this is also interesting topic. Okay, with that in mind, what we want to do now, as I said, is to reduce number of your inputs, of your features, and preferably that would be nice to have significant reduce. Like, for example, here an example of text processing where you have, let's say, that is 10,000 of words converted, and you can, well, if you have 10,000 of words, you can imagine how many different texts you can make by combining different variations of 10,000 of words, yes? So each word is one of the possible words. A lot of, I don't know, in different languages there are different amount of words in general, yes? Some are more rich in words, some are less rich in words, but still it's measured in tens of thousands, I believe, for most languages, yes? And accordingly now you want to create a combinations of tens of thousands of the length of the tens of thousands. So that brings you almost infinity of possible combinations for this space, which you want now to convert into three-dimensional space, let's say that, which you can actually picture that this text looks like this point on this three-dimensional space, another text will look like this point, another text will look like this point, etc., etc. So you convert these 10,000 dimensions into 3 dimensions, and then you can even display them in the different points in 3-dimensional space. Now, the problem is that there are also infinitely large amount of such k-dimensional subspaces. Yes, so which particular three dimensions should we choose, as there are almost infinity of different options for us to choose from. So how are we supposed to find the most suitable one, which preferably will preserve the structure, preferably will not change the accuracy of your prediction, etc., etc. So how exactly are we supposed to understand that? There are multiple algorithms for that, which we will cover today, but sufficient to say that it's of course depending on what exactly you want to do. So let's say you are working with classification and want to predict some objects based on, for example, pictures, or for example some user data or something else. Yes. Now, in that particular case, a technique that can be used for that is, for example, linear discriminant analysis. Yes. Now, if you are working with a regression, that is forecasting weather or predicting prices or maybe stock analysis and stuff like that, then in this particular case, what we want to use instead is partial least squares method. And also you can use this for unsupervised problems when you need to create certain clusters, and that's exactly what we are going to focus more on today, because it's quite common to actually, okay, let's say you have some data set, you have 1 million of inputs, and you don't really want to work with that data set. First, you want to narrow down these inputs, and because of that, since you don't necessarily have labels, yes, so it's working like that. Okay, you have this data set, this is x1 all the way up to x1 million. And you don't have any y's, unfortunately, because, well, we can't say that you are too lazy to analyze these, let's say, also 1 million by 1 million data amount, but we can't really say that it's laziness, it's reasonable hesitation, yes, to do so. To, okay, first example, I'm going to check all these, okay, then that is class 1, for example. So that is something you have to do manually yourself, which obviously in this particular case you really don't want to do, yes. So instead, what you are going to say, okay, let us now instead use dimensional reduction technique to create some other inputs. Let's call them x asterisk 1, x asterisk 2, all the way up to, let's say, x asterisk 10, which are combinations of your original x1, x2, x3, and so on. Yes, so now for this amount of data, it will be much easier for you to create this label. So before you actually add labels, sometimes you really want to first treat your problem as unsupervised, then reduce dimensions. So we start with unsupervised, then reduce dimensions, then create labels, which is often also a process of this dimensionality reduction as well, and only then we want to treat this problem as a supervised to, let's say, train a neural network, for example. So that's an approach you can use to avoid unnecessarily large amount of work. So, and principal component analysis here is a powerful tool for you to consider if you want to do something like that, which we will then cover today in the lecture as well. So, but first let's work with this linear discriminant analysis, because here you actually do have correct answers. For example, here you have two, not really clusters, two classes of data, the red dots and the blue dots. And you already know which are which. So what we want to do now is to somehow make these two classes more distinguished, that it will be easier for you to make classification without having these points like here, yes, as you can see, some uncertainty is here because your distributions of each of these points actually overlap here. Yes, so what we want to do now is to have this overlap gone and distinguishable clear boundary between these two classes. Yes, so that is something you can use linear discriminant analysis, which is making projections of these points. So what essentially what it does in this example is it has certain line constructed. Yes, so let's take this line, and it makes projections of your data onto these lines. For every point, now it creates a projection. And now it is only a matter of finding whichever line is the best one. Is it this line? Maybe, I don't know, maybe this line, maybe some other line like this. So whichever line is going to have the best difference between projections, which happens to be in this particular example, specifically this line, as producing the most distinguished class as different projections. Yes, as you can see, what we are factically doing here is trying to find the best line, but it is not a specific linear regression problem when you try to make, or classification problem when you try to find this boundary and then decide whichever is above, whichever is below, and accordingly speed. But instead, we are thinking in terms of your data points projections onto this line. So not necessarily we want a good line that separates them, we want a good line that projecting to this line for these projections is having the good separation. So as you can see, for this line, our projections colored in red and performed as distributions overlap here, whereas for this line, each projections which are orthogonal from this point, orthogonal to this line, are actually much better distinguished. And this is example for 2 dimensions. Needless to say, the same stuff can be done easily for more than 2 dimensions. For 3, for 4, it's just that we will not be able to picture that so nicely. Yes, and that's why specifically this example has 2 dimensions, because it is easy to show the idea. You search for this line for hyperplane or whatever else, yes, that produces these projections. Now, let's say what we have is this conversion of 3 dimensions to 2 dimensions. This is actually quite opposite to the support vector machine which we were discussing. Yes, if you recall, support vector machine was actually doing quite opposite things. So let's say you had 5 dimensions, and then support vector machine, by using a kernel function, created let's say 8 dimensions, and if your data was not separatable well in 5 dimensions, then it was quite well separatable in 8 dimensions. Now, dimensionality reduction actually does quite the opposite. So here, again, as I said, we were considering for supervised case, yes, when you actually have correct labels, and you know that this is class 0 and this is class 1. And hence, you can easily say how well are they separated for each of these lines as projections, here and here and here. But what if you do not know these labels and you have unsupervised dimensional reduction problem? So as we have seen here, yes, we are going to use something called principal component analysis, which effectively remains the same. However, our criteria for choosing this line, and in fact actually multiple lines, as you will see, now is different. So And we are back to that example which I was discussing here, because in this picture, particularly here, you can see that although we have a three-dimensional space, the majority of the data is focused in certain plane. Yes, so you can see some plane in 3 dimensions where, as a sheet of paper, you have certain points, and the question is, do you really need 3 dimensions here or not? Now, it's not as easy as to say, okay, if it is 2-dimensional data, actually let's then cancel out one of the axes. Let's say remove axis z. And, well, it's quite close to what we actually are doing, that except that you are not going to simply remove axis z, but you are going to remove axis z and project every point to the other axis x and y as projections, which are going to produce some new dimensions. In addition to that, we are also going to consider the density of points. So as you recall, we were discussing some unsupervised algorithm db-scan, which is density-based algorithm, which was using variation to determine where you have cluster and where you have not. This is quite commonly used method. This is a method we are also going to use in our next practical exercise. And what is important to notice here is that it actually cares about the variance of data. Yes, so it tries to find such axes so that the variance is as large as possible. It tries to keep it, well, it's possible to the same level. So how exactly that is working? So let's say we have 2-dimensional data here, yes, consisting of x1 and x2. We don't know these classes, so because of that, every point here is of the same color. Yes, we don't know which is class 1, which is class 2, which is class 3. Just no information of that. And what we are now going to try to do is to find some new axis for which we have as high variation as possible maintained. Yes. So, for example, we are going to change our axis x1 into some axis, let's say z1, axis x2 into some axis z2, in such a way so that we have as high variation as possible. So again, we are quite back to this same pattern as here, yes, that you are now trying to project every point. Well, actually, let me show this on this example. Like this point is then projected here, this point is then projected here, this one here, and so on. So every point is therefore projected onto the corresponding axis, yes? And then what you are interested to know, what is the variance, that is range, in which your value changes over this axis. So this gives you certain measurable criteria as to understand whether your axis is good or not exactly, yes? So here we can see that Z1 axis has a variance of the, how it says, of this projection in around here. No, sorry, it's actually axis Z2. I wanted axis Z1. So the variance from this point all the way up to variance from this point. So that is the total variance of the points projections onto the axis Z1, which is more than it was for x1. Yes? You can see that clearly, that this range is more than this range, without doubt. Yes? So the goal is to find such axis Z1 so that this variance, this range in which it can happen, is maximum, as large as possible. Yes. When you are done with this, you find next axis, which is the second best. Yes. So the second best in this case was Z2 axis, which happens to have variance of this, and so on, and you continue. So basically, each new axis will have smaller and smaller variance, and accordingly less and less importance. Yes, because we consider that this variance is actually a measure of importance of this parameter. And because of that, once you have, let me a little bit scroll ahead, once you have this accumulated as for the first axis variance is like here, for the second axis variance is like here, for the third axis variance is like here, and then you define certain threshold, okay, I'm going to say like 5% is the critical value for my important variance, yes, and anything that's below is going to go away. That means that you will have only 3 dimensions in this particular example, just because others, well actually sorry, 4 dimensions, principal component 1, component 2, component 3, and component 4, because other dimensions do not really provide sufficient variance to your data, and you say, okay, it's not going to be very accurate, but we lose not so much of this variance, so we can say that in a sense we are almost precisely describing our data set, but instead of 10 inputs, you are now going to focus on 4 most relevant ones, yes? And that is the idea. That's how you are actually doing that. So, of course, behind this there are quite complicated mathematics, which let me try to explain briefly. Yes, what is the idea of how exactly it is done? And accordingly, that is run by a simple algorithm in Python environment, which means you don't really have to program it yourself, but the idea is like here. So here you can see 3 examples of 3 lines. Let's try to see what is the variance for each of them. So for this, let me mark it with a blue color, not blue, but green color. For this line, the variance of the data is from this point all the way up to, I believe, this point. So it is like so. For this line, the variance of all of these projections from this point all the way up to this point is like here, and for the red one it is from this point all the way up to this point, which is here. So as you can see, again, for example, for me it might not be so obvious, maybe for some of you it's easier to see that the red line is longer than green and the yellow one, but if you actually measure this as the minimum to maximum and find the distance, max minus mean, for each of them. Yes, max minus mean, and also max minus mean. Then this one is going to be the highest value. So we also have some precise tools to actually consider that. That's how you construct one axis. Yeah, just one axis. After you have constructed this axis, your points are going to be distributed around this axis only, like so, yes? And what we want to do next is to find the next axis that also as high variance as possible, yes, provides for it. Well, it's not continued here, yes, but in a sense, sorry, it's going to be something like, I don't know, difficult to imagine. That's going to be something like that, maybe. Yes. But again, I'm not claiming that this is actually the best line that provides the most variance. Yes, maybe there is a better one, and that's exactly what this algorithm does. It calculates it precisely. It doesn't try to guess it. It uses formulas. It uses linear algebra, matrix multiplications, and all that stuff to figure it out. Yes. So we will have another algorithm suitable for this as well, and I will refer to their differences, but this one is actually optimizing this stuff. Yes, it's as if you imagine, let's say you have a room and you try to put some furniture in your room with the goal of having the maximum free area. So what it does, it then says, okay, I'm going to put a dresser here because it is the biggest one and, well, my room is currently empty. Now it tries to figure out where should I put the table. Maybe here, then I will have the remaining area like so. Maybe somehow overlap this with dresser. Then I will have another area. So it actually goes through options and optimizes it. Yes? So how exactly does that work? Well, in order for that to work, you really need to have all the possible variations, all the possible stuff. And for that, you need to calculate something called covariance matrix. Now, this is very similar to correlation, and I'm not sure if you did cover this in probability theory, covariance, or not exactly. Well, at least I think it might be a topic for your probability theory. But let me just show you first some example of how exactly this covariance matrix is performed. So let's say I did have some example data here with some numbers which I can use to demonstrate for you. Let's say you now have 3 inputs, 3 columns of data, x1, x2, and x3. Yes, now x1 are 2, 4, 6, and 8. x2 are 1, 3, 5, 7, and x3 are 10, 15, 20, and 25. So now I'm going to show you an example how are we supposed to calculate this covariance matrix and how we can use it afterwards. Now, it is really simple actually. Yes, I can use this. So first, what you are now going to need to do is to calculate the average for each column. Mu x1, mu x2, mu x3. Well, this is quite simple. You add them together. That is 6, 12, 20 divided by 4, 5. Now it is 4, 9, 16, 4. And this one is 30 plus 40, 70 divided by 4. That is 70 divided by 4. Well, it's 17.5, something like that, right? Then you subtract these average values from each of these and create a new version, x1, x2, x3, average centered ones without the mean, that is going to have minus 3, minus 1, 1, and 3. Here it's going to be minus 3, minus 1, 1, and 3. And here it is going to be minus 7.5, minus 2.5, plus 2.5, and 7.5 here. Okay, so now we have removed mean from each column. Then we can calculate a covariance between any combination, for example, covariance between x1 and x1, or covariance between x1 and x2 in all the possible ways, like x1 and x3, x2 and x2, x2 and x3, etc., etc. And each of these covariances is calculated as the average of xi minus mu xi multiplied by, well, it's not exactly these brackets. Xj minus mu xj. So in a sense, that means, for example, if I want to calculate variance between x1 and x1, or I'm sorry, covariance between x1 and x1, which will actually be a variance, which you know from probability theory that is going to be x1I minus mu x1I multiplied by x1I minus mu x1I summation and divided by n. This is a plain formula of variance because these brackets and these brackets are the same, and hence you can write it as follows, that this is a square, yes, which is the variance of x1. Now, if you will take x1 and x2, they are not the same, so instead of calculating variance, you will calculate covariance between x1 and x2, and it's calculated just like that. So what that means is that, let's see for example. So that means I need to take this column and find its, well, okay, maybe let's take x1 and x2 instead, because having the same column is not fun, yes? Let's say x1 and, well, numbers are actually the same. So anyway, these two. So what I need to do now is to calculate minus 3 by minus 3. So let me write that in different color, minus 3 plus minus 1 plus 1 plus 1 plus 3 plus 3, and divide all of that by 4. So that is going to be around 0. Well, something I have calculated here may be a little bit slightly wrong, but anyway, you calculate all these combinations between each other. Wait, no, actually they have to be products. I'm sorry. They need to be products, minus 3 by minus 3, minus 1 by minus 1, 1 by 1, 3 by plus 3. So here we have 9, here we have 1, 1, 9, add together, that is 20 divided by 4, that is 5. Yes? And of course, having a combination between x2 and x1, yes, is going to be also 5, yes, because order here doesn't matter. So anyway, this way you can construct this covariation matrix. That's how it's working. And in Python you can use as simple as numpy cov of your matrix X transpose to do this operation. Yes, so again, you don't really have to calculate it manually. I just wanted to explain exactly what it is. So you calculate the variance by finding the column with itself, and you calculate the covariance by calculating any two different columns between each other. Yes. So next step is, okay, we now have this covariance matrix, yes, which is basically, you can think of it as a certain indicator of how large is the variance between x1 and x2, how large is the variance between x2 and x3, and so on, which is exactly what we are interested to know. We want to maximize this variance, yes. Now, inside of this matrix, yes, what we will want now to do is to find certain x's, yes, which are called eigenvectors. Well, I'm a little bit oversimplifying it here intentionally, yes, because it's actually not going to look like this straight line, but the idea is nonetheless the same, that there are certain directions, like a diagonal matrix, where you have a highest variance, yes, and in others it's not. You can think of it as some I don't know, rubber sheet, yes, which you can now try to stretch in different dimensions, and in some dimensions it will stretch more than in others. So those dimensions in which it can stretch more are eigenvectors, and those dimensions which almost doesn't stretch at all, yes, are accordingly not eigenvectors. And accordingly, each of these eigenvectors is also assigned, so you have eigenvector AV1, eigenvector AV2, each of them is assigned a specific single eigenvalue, which is actually your variance. So, having this eigenvalue, you also understand which eigenvector is giving more variance to your data than others. Yes? So, in a sense, allowing you to choose which eigenvectors you want to keep, and basically each of these eigenvectors is exactly this kind of line. Yes? But it is optimal line, the red one. And then you construct next one, and next one, and next one, and next one, and so on and so on. And, well, that is the idea, yes? And if we now try to write down the solution, just give me a moment, please. I had it over here. Not in this presentation, unfortunately, yes. So, let's say you have your data matrix X, and accordingly is your data. Now, how we were supposed to denote eigenvector. So eigenvector is nu and according agent value is lambda, matching this eigenvector. So then you can say, and well, actually this x data is not exactly x, it's our variance, yes? So how it's denoted here, it's that sigma. So this is our covariance matrix. And the good thing about covariance matrix is that it is symmetric, meaning that your diagonals are the same, and it also is a square, always, yes? It just cannot be non-square. So again, this is very good for us because this allows you to find some inverse, some solutions and all that stuff, which otherwise not necessarily would be possible. And what we want to do now is to solve this kind of equation, and that is exactly what this principal component algorithm does, is it finds a certain lambda values so that you can replace the entire covariation matrix with just one number of eigenvalues. So eigenvalue effectively gives you the same result as this entire covariance matrix. And you can find it analytically. You don't have to write some gradient descent algorithm or stuff like that by solving the equation, yes? So like this, that would be sigma minus lambda identity matrix equal to 0. So that's how you can calculate the eigenvalues. Yes, so that's how you find these lambdas. And then, after you have these eigenvalues, you can find the corresponding vector simply by multiplying it. Yes, so that is sigma minus lambda I multiplied by mu equal to 0. Then, from here you find also the eigenvector. So this is actually analytical solution. Yes, this is not search of certain form. It doesn't include any randomness. Yes, it's a very exact and strict algorithm, which is computationally intensive, yes, it asks quite a lot to analyze all these eigenvectors, especially if your covariance matrix becomes more and more, which covariance matrix size is solely affected by how many inputs you have, x1, x2, x3, x4, x5, by x1, x2, x3, x4, x5. Yes, so that's again the point to reduce these dimensions. Yes, but still original data will have, let's say, 1 million of inputs, so you will have covariance matrix of 1 million by 1 million, and you will need to find these solutions for this large matrix. So of course that becomes computationally expensive, yes, and difficult to do. But the general thing here is that what you are doing is then you reconstruct your entire data set onto these eigenvectors. Yes, so these eigenvectors are these axes. Yes, well, we can think of them in multi-dimensions. Yes, there are like 5 or 6 dimensions, for example, in which they are all orthogonal to each other. So this is orthogonal to this is also orthogonal, this is also orthogonal. It's difficult to show, maybe, well, just to show you in 3 dimensions instead. Yes, so orthogonal, 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 yes, which are not necessarily the same as your original x, y, and z, yes, but more taking into consideration the variance along each of these new axes, yes. And again, the most important point here is that originally you had not 3 of these axes, but let's say 1 million of these blue axes, which I cannot simply display, yes, because it's difficult to imagine that many dimensions. And the red ones you will have much less. Actually, let's say 3, yes. So you convert 1 million of axes into 3 most important axes for which the variance is maximum, which you actually find out by calculating this covariance matrix, eigenvectors, and eigenvalues. Yes, that's how exactly it is done. And then, when you have calculated all of these eigenvectors, let's say in this example we have calculated 10 eigenvectors and 10 eigenvalues, each of these eigenvalues then can be used to actually tell you how important is that vector, how important is that axis you have decided to use. When you make some threshold of certain critical value, like 5% for example in this case, yes, then you see that only first 4 vectors produce sufficient variance of your data to consider them to be used, and all the others are not so important. Of course, they will add more accuracy to your algorithm, they will add more similarity to your data, how it looks before and after, but in general it's not a big deal if you discard them, and your algorithm might become actually working better because you will avoid some overfitting. You can think of it as missing some of the values or regularization. So here you can see some example of residual between the original picture and the compressed one with a PCA. Yeah? So here you can see original input, here you can see the average, which is the blurred version of this picture, and accordingly the more number of components you are going to use, the more similar your output becomes to the input, and vice versa. The less number of components you use, the more similar it actually is to this mean. Yeah? So if you compare these 2 pictures, they are very similar, whereas these 2 are more similar. But still, can we tell from this picture that this is a number of 3 if, for example, this was having 20 by 20, 400 pixels, yes? So here you can see a clear example that we converted our picture consisting of 400 features into a picture of 100 features, and still can decide that this is actually 3. So your requirements towards your algorithm reduced, you avoid some overfitting, and you also run it faster because you have much less inputs, and accordingly you can even maybe afford even smaller neural network because of that. Okay, with that in mind, there is also example of images more complicated than handwritten digits, like for example faces of people. Yes, here you can see that, well, first one is, well, I don't know if you can see from there or not, but it is very blurred picture. It's actually average, yes, so it's blurred picture. And then there are 15 agent pictures, yes. Well, agent picture corresponds to the agent vector here, yes. So agent picture 1, agent picture 2, agent picture 3, all the way up to agent picture 15, and this is average, yes. So each of them can be packed or unpacked as a single vector, just like we did in our neural network program, yes. And well, because these agent vectors are actually showing some phases, yes, even on these levels, yes, as you can see, they are called like agent phase. So what is the idea here is identification of a person depending on the picture. So in all of these pictures there is the same person, however the face expression is different, and some pictures I'm not probably seeing in here, but some pictures this person is wearing glasses, some pictures not, yes. Same goes for some other accessories might be, yes, but still the algorithm would recognize that person as the same person in all the pictures, yes. So this is important for systems such as Face ID, yes, like your smartphone might be using when you use frontal camera to unlock it without having, you know, to input code or maybe use your fingerprints and stuff like that, yes. So different expressions, variations, and all that stuff still can recognize the same face, yes. Why? Because we extracted only the most important parts of this face that are making this face belonging to this person, without specific details as to what is the current light. Is it daytime? Is it nighttime? Is it natural light? Is it artificial light? Is the person wearing glasses? What is the haircut of this person? And all that stuff are not so relevant parameters as to specific most important agent vectors of these images, yes? Now, of course, everything is always coming with the price, yes, and we can say that this is quite intensive algorithm, and well, it might be difficult. For example, if you have image of 32,000 pixels on each axis, you can imagine how large that number is. And finding all agent vectors for such matrix with these dimensions will take some time. Now, what you need to consider here is that this is a very accurate algorithm, just like in a linear regression. When we started, we said that there are two ways to do this task. First way is to run the gradient descent, which is iterative, and with each next iteration it converges to the final solution if done properly. And another one is normal equations method, where you have a formula, you input that in Python, run it, and it always in one go produces the result. However, it needs to calculate some inverse matrix. It relies largely on how big is your data set, and accordingly, the greater is your data set, the more favorable becomes gradient descent, and less optional is the normal equation. Similar happens here. So here we can use some methods which we discussed last lecture to decompose the matrix into smaller matrices. Yes, so singular value decomposition, yes, has your large matrix split into 3 smaller matrices, with which it is easier to operate. Yes. So we already seen this kind of a picture in the last lecture, yes. So again, here comes this idea that you want to convert this otherwise inconvenient and large matrix into smaller matrices. And for that, use certain randomization, of course, yes. It's not maybe exactly always best idea to calculate the precise X values, but the main thing here is that one of these matrices, which we will calculate, is well, R eigenvectors. Yes, eigenvector 1, eigenvector 2, eigenvector 3, eigenvector 4, and so on. So we can use singular value decomposition algorithm to find out these eigenvectors. And once you have these eigenvectors, you can also find the eigenvalues, yes, which are stored in this matrix. And your original matrix is, for example, your data or your covariation matrix. Well, it actually depends, yes. So maybe I won't really focus much here, yes. But the idea is that what you want to do is to solve these equations, this matrix of equation, yes, to find out this one, yes, and also this one. Then once you have this matrix V, that is eigenvectors, then you select the most important ones, K, which you construct by ranking them like this, yes, and specifying certain threshold. So here you can see that we used 4 components only, and accordingly that is the solution. So in a sense you can say that this is the way to calculate your principal component algorithm. They are not exactly the same, yes, but more or less it's one of the ways to run this algorithm on a computer. Okay, so now if we already have the data set labeled, so we have supervised problem, let me remind you that the PCA, principal component analysis, was used for unsupervised, meaning that you had no labels, no correct answers. Now, if you have supervised problem, then that means you have labels already. Let's say for handwritten digits, they are labeled. This is a picture of 1, this is picture of 2, etc., etc. Then you can use, instead of PCA, another approach called partial least squares, which is very similar, but it actually works differently, yes? So what happens here is that now, instead of having to run some complicated mathematical formula for finding this perfect line with the highest variance, what we are going to do is to use the algorithm we already know, called a linear regression. So then we construct this line by running the linear regression of this line. Yes, so we can do that. We already know that. This was actually one of the first algorithms that we have studied. And well, the only reason why we didn't do that for PCA is that your linear regression requires to know your outputs y, whereas in PCA algorithm we don't have these outputs y. We don't know the correct answers, and you cannot use linear regression there because of that. Here, in supervised problem, we do know the correct answers y, and because of that, we can actually approximate this line by linear regression. What happens then is we find the difference between this linear regression and these points. So that is error. Or maybe not exactly error, let's call it residual in this case. Yes? And for this residual, you continue the same operation. So you can think of this as rotating this picture now and finding and compressing it a little bit, yes, and finding the next line, the next linear regression for that has been processed like this. So the idea is quite simple. First, you find, first you have y and x data, x and y. Second, you find the hypothesis of linear regression. Third, you find difference, residual. then you use this difference residual, so hypothesis 1, yes, hypothesis 1, instead of y, to find hypothesis 2, etc., etc. So next, this is how we find these components. Each of these components is a linear regression of what is left after the first linear regression, what is left after the second linear regression, and so on. And you can see here even that in this slide we have comparison between linear regression, solid line, and principal component, first component. Yes, this is a dotted line. Okay. Another approach, which is much less computationally demanding, cheaper, but also it is random. Yes, it's not any more deterministic like it was for PCA component analysis. Yes, which was always producing the same solution. No matter how many times we run it, it's the same solution. Now here we make the random projection of certain inputs. So basically, we don't even try, yes, to optimize variance. So we don't care about variance anymore. And what we want to do is to keep the structure of the data with as small difference as possible. Yes? So instead of optimizing variance, we then care about the structure of the data more. Now you can think of it as the, let's say, equivalent if we try again and say, okay, for the principal component analysis, in the example I have mentioned about the furniture, you have a certain room with a certain area, and you try to put your furniture as best as it can by calculating all the possible variations, distances, all of that stuff, to leave as much free space as possible. Yes, that's how PCA analysis component works. It actually optimizes the problem, whereas random subspace projector, let's call it RSP for short, yes, would solve the same problem differently. What it will do, it will take and throw it randomly. One is here, one is here, one is here, and see if it suits your needs. If not, it will try another option. If not, again. So basically, it makes some random allocations, hoping that it's going to hit one that will be good. Yes. Again, considering how many attempts you may need to do, it still may be faster than actually performing the full-scale optimization, especially if you have a lot of this furniture to consider, yes, especially a lot of small furniture, yes, which again won't matter if you are speaking about some small boxes. Will they be in your, I don't know, dresser or on your table? In a sense that will not affect much, yes, but having to optimize each of the small boxes, yes, is going to put a high toll on your system and require a lot of time, whereas in randomization case, it may turn out to be okay, yes, for most of the objects, and you will need to focus only on the largest objects of your furniture instead, yes. So that is the analogy between random subspace projection and the principal component analysis. Now, all of these methods that we have covered so far were linear ones. Yes? So where that was, just a minute. Linear combinations, meaning that your output, let's call it Zi, actually was a certain combination of x inputs. Yes, x2, x5 maybe, x7, and so on. So you actually took one input, another input, third input, and combined them into one input. In a non-linear case, this is a certain non-linear function, not addition, yes, of your x1, x2, x3. This may be a product, for example, multiplication of this feature, or maybe they even are not exactly resembling. Yes, maybe you create a new set of features which in no way are relevant to what was before. So that is nonlinear combination. And for nonlinear combination, there are two algorithms that I'm going to cover today. Yes. One of them is isomap, yes, isometric feature mapping, and another one is T-stochastic neighbor embedding, or TSNE, yes. So what is this isomap and what is the idea? So consider this three-dimensional data, and that you need to find all the way from this point here up to this point by following this data structure, not directly like here, which is called Euclidean metric. That is not what we want. What we want is to follow all the data pattern and find the geodetic distance. That's how exactly, for example, we calculate. Imagine you have the Earth here. Well, I'm not so good at drawing, but here you have some Europe, here you have United States maybe, yes. And what you want to do is to find the distance from Riga to New York. As you know, the Earth is a spheroid, yes, and if you try to calculate this as a straight line, you will go straight through the Earth, yes, which is not accurate distance, and instead you have to actually take into consideration the curvature of the Earth. Yes, that's exactly what happens here, and that's exactly how it can happen in more dimensions than 3, yes. So this idea is exactly similar, yeah, and isomap is one of the algorithms that can, just like for the Earth, yes, we can display that on 2 dimensions as a map, yes, or in 3 dimensions as a globe. The similar way, isomap algorithm can unwrap your multidimensional picture into less number of dimensions, like you can see here, 3 dimensions became 2 dimensions, yes, and then you can find this distance in 2 dimensions as well, just like it was happening here. Yes, so that is the idea of this non-linear feature extractions. Yes, it keeps the global geometry. Yes, that's important because the second algorithm will focus more on local clusters, on groups, yes, but this one tries to keep them more global. Again, just exactly like the Earth on the map. Yes, we try to, show our continents, our seas and all that stuff as relevant as possible as to what they really are, but considering, of course, we only have 2 dimensions instead of 3. And keeping the distances is the most important part here, just like keeping the correct distance between Riga and New York on the map, yes? Now, I'm probably not going to delve deep into this isomap one, yes, just to show some more examples of these, like, for example, classifying the pictures, yes, so each of these pictures originally was certain number of pixels, let's say for simplicity 10,000 pixels, yes, and what we wanted to do is to convert each of these pictures. This could have been also pictures of 1s, 2s, 3s, etc., yes, which we were using, into points in 2 dimensions, yes, so each of them is therefore located in some 2-dimensional space. So you converted this picture into x and y, 2 coordinates, which allows you to put it as a point here, 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 yes? So from, here it actually says it's actually 4096 dimensions originally, which means that it was around 256 probably, or something like that, pixels per 256, and you have converted that all into 2 parameters. That is also possible, yes, for handwritten digits, and you can see them, then you can actually group them, yes? Here you can see digits 2, but digits 5 will be somewhere there. Digits 4 will be somewhere there, etc., etc. So they will be somewhat clustered in these 2 dimensions as well. Yes? Now, another approach is to use a t-stochastics neighbor embedded. So the general idea is now what you are using instead of this distance between these points is the probabilities, yes? So here you can see how we have converted into 2 dimensions our handwritten digits like 1 or 2 or 3, which is called MNIST dataset, yes, which we were using. And we have 20 by 20 pixels, so that is total of 400 pixels for each picture, and we convert that into 2-dimensional picture. So you convert 400 pixels into 2 numbers, yes? And then here you can see that TSNE algorithm was able to distinguish these clusters better, whereas ISOMAP was more focused on the global pattern of data, yes? So here you can see the difference. TSNE is actually focusing on making correct clusters, yes? So this is clusters of handwritten digit 3, this is cluster, no, this is 4, this is 3, this is 5, this is 6, represented in 2 dimensions like a picture, yes? Which otherwise would be quite difficult to do with these images, yes? Consisting of 20 by 20 pixels. So if you need to focus on some cluster structure, then TSNE is better. It's using something called p-probability distribution, yes, to describe these probabilities of belonging to the correct clusters. Whereas if you need to find certain distances over, let's say, the Earth surface, yes, or in multidimensional space in some imaginable tunnel or something like that, then that is ISOMAP for you to use. Now, we might try to use TSNE just to visualize your handwritten digits like this, but I will see if it's as easy as it seems, because, well, it seems easy once somebody has constructed this picture, but there are certain parameters that you need to input, and TSNE algorithm is very demanding to the correct parameters. So if you, unless you specify correct parameters, then it might be difficult. But I'll try my best to see if we can actually visualize our data as well in such manner. Now, if you are interested to see more mathematics, yes, and all that stuff, you can follow more links. And also, if you are interested to try out this in MATLAB, there is a toolbox for that. But other than that, we'll try that on the next practical exercise as one of the steps. Yes, so we will have next practical exercise focusing on reinforced machine learning algorithms, for which one of the steps we will try to do this principal component analysis to see the difference when you use that and when you don't. So how is the accuracy and how is the computational complexity, we can say like that. Okay, that is for today's class it. If you have any questions, please don't hesitate to ask, and if you need to mark your attendance, you can also do it now. Thank you, and see one of your groups on the practical exercise, another one next week then.